So let's do two more examples here of optimization for the section 3.4. And let's begin with one that was similar to the one that we started off in the last video. Once again, with a rectangle. So let's look at this problem here. All right, so for this problem, it tells us the supposed homeowner is planning to build, once again, a rectangular garden in front of their house. So here we're doing a rectangle once again. And suppose the material needed in order to build this garden costs $2 a foot for the side along the house and the adjacent sides. All right, so it's going to cost $2 for the side along the house and the side on the left and the side on the right, $2 a piece, $2 a foot. But then it's going to cost the material that we need for the side along the driveway will cost $6 a foot for the side along the driveway. All right, so here we have the side here on the bottom, on the opposite from the house, but along the driveway. So the driveway will be in front of this garden. And so what type of house is this? We have a driveway in front of a garden, part of the house from the change lane. All right, so it's George C. Scott is going to build this garden in front of their home here. And suppose for this garden we're trying to build, we want it to be 5,000 feet squared. And so we want this garden to be 5,000 feet squared. What does feet squared mean? That the area has to be 5,000 feet. Okay, again, squared units means area. And what we're trying to figure out for this case is, what should be the minimum cost in order to build this garden? So here we're trying to minimize the cost of this garden. Okay. So let's look at what's given to us here. Or actually, let's first figure out what is it that we're trying to optimize, or in this case, minimize. We want to minimize the cost that it will take to build this garden. And to build this garden, we need the material that will surround the sides of the garden. $2 a foot for these two sides on the left and the right, but also $2 a foot for the top side. But then it's going to cost us $6 a foot for the material needed to build this side on the bottom here. So for this problem, we want to minimize cost. So here we got to develop a cost function to represent how much we're going to spend for the items, for the material that's needed for the sides of this garden. Okay, so let's set up our cost function here. Okay, so our cost function, well, what do we need to know? If it's going to cost us $2 a foot here for the left and right, if it's going to be $2 per foot, then we need to figure out first how many feet, how long the left and the right side are going to be. Let's call that X. I'll give it a red color. So let's call that X, the length of this left side and the length on the right side. Okay, but we also got to figure out how long is this top side going to be. And for the top side, it's going to cost us $2 per foot. So for the top side, let's call that Y. Okay, but this top side and the bottom side are going to be of equal length. So this will also be Y on the bottom. All right, so we have X for the left, X for the right, Y on top, Y on the bottom. So we're going to figure out how long each side is going to be to figure out how much to spend on each side. So how can we figure out then our total costs? Well, our total cost is going to be the length of each side times the respective price. In other words, it's going to be 2 times the left side, so let's call that 2x. All right, the length of the left side times how much it's going to cost per foot, so how many feet on the left side, times 2, plus the side on the bottom, the length is represented by y, and that length is going to cost us $6 per foot, so 6 times y. Plus the side on the right side, twice per foot, where x represents the length of that side, so 2 times x, plus the cost of the top side, where it's going to cost us $2 per foot, and the number of feet of the top side is represented by y, so plus 2 times y. All right, combining like terms gives us a total cost here of a 4x plus 8y. So that's going to be our total cost function. Okay, and this is the function that we want to minimize. And this is the function that we're trying to optimize. But what's the problem? Similar to the example from the previous video, the problem is that our cost function is in terms of 2 variables here, x and y. We have to make sure that in terms of, if we want to find a derivative and the critical value, we got to rewrite in terms of just 1 variable. So how can we do that? Well, what given information do we know about this garden that we're trying to build? We know that the garden we're trying to build has to be 5,000 feet squared. That the area on the inside has to be 5,000 feet squared. Meaning, when we find the area by multiplying x times y, the inside should be 5,000. All right, so here we're given that the area should equal 5,000 feet squared. And again, how do we find the area of a rectangle? By just taking x times y. So x times y should equal 5,000. Okay, so what can we use this for now? What can we use this equation that we have here on the right side? Well, we can use this to help us rewrite the function that we're trying to optimize in terms of just 1 variable. All right, so let's see, for x, 8y, let's use this given information and let's solve for x. So dividing both sides by y, it's going to give us x equals 5,000 divided by y. And now let's take this and plug it in to x here. All right, so we're going to write our function here in terms of y. All right, so let's rewrite our cost function as c equals, did I use a different color? Hold on, let me just double check how to do that. Yeah, I used a different color. All right, so let's write that as c equals 4 times x, which can be substituted by 5,000 over y, plus 8 times y. All right, to give us, let's see, what does that give us here? It gives us 20,000 over y plus 8y as our cost function in terms of just 1 variable. Okay, so now we have this function in terms of just 1 single variable. So in the next step is to find its derivative so we can optimize it. But before we do that, let's rewrite this first term here and bring y to the top. So let's rewrite this. That's 20,000 times y to the -1. Right, to bring this denominator to the top, we gotta change the sign of its power, plus 8y. Okay. So now, just want to make sure, yeah. So now Time to optimize that function. Again, to optimize means to find its derivative and its critical value. So we're going to take c prime, the derivative of the first term, bring the power down, decrease the power by 1, gives us negative 20,000 times y to the negative 2, plus derivative of 8y is just 8. Okay. So now let's set this equal to 0. And for this first term here, let me bring this down. Let me make this power of y positive. We're going to have negative 20,000 divided by y squared plus 8. Okay, and now we're going to do a bit of algebra here. Let's move 8 to the other side. Let's subtract 8 from both sides. So we're going to have negative 8 equal negative 20,000 divided by y squared. Let's multiply both sides by y squared so we can have it on top. So multiply the left side and right side by y squared. I can multiply this by y squared, multiply that by y squared. They cancel out here. And on the left side, we have negative 8y squared equal negative 20,000. Okay. Let's see here. All right, so now we're going to take 20,000 or negative 20,000 divided by negative 8 to give us, would that be 50? Yeah, that would be actually 2,500. So negative 20,000, divide that by negative 8, gives us y squared of 2,500. Oops. And now we're going to square root both sides. I'll just write that. So now we're going to square root both sides because we have the squares. The squares cancel out. And we get that y equals either negative 50 or positive 50. Again, we just square root. And so when it comes to square root in some equation, we have to consider the negative and positive root. So which one would it be then? Well, let's get at the context of the problem. What are we looking for? The length of this side of the garden here, the top and bottom side. Can length be a negative number? Length cannot be a negative number. We're going to take at the context of the problem. So it cannot be negative 50, which means that y, the side of the top and the bottom, has to be 50 feet each. Okay. So now that we know the side of the top and bottom, now we're going to figure out the side on the left and the right. And how do we do that? By taking what we just found here and plugging in into the equation that we have on top here that is solved for x. Okay, so now we're going to take x equal 5,000 divided by y, and which we got y to be 50. So 5,000 divided by 50 gives us x equals 100 feet. Okay, so the left side and the right side should be 100 feet each, and in the top and the bottom side should be 50 feet each. Okay, but not finished just yet, because what is the question asking? What's going to be our minimum cost? So now that we know the length, now that we know the dimensions of the garden, how can we figure out what our minimum cost has to be? By plugging in these two values into our cost function. Plug in the length of x and the length of y to figure out what our cost is going to be at these two dimensions. All right, so now, again, our cost function, kind of run out of room here, I'll put it here. So our cost function was 4 times x plus 8 times y. And if we want to minimize this cost, x should be 100 foot. and y should be 50 feet. So 800, oops. So 4 times 100 plus 8 times 50 gives us a minimum cost, pretty cheap here, a minimum cost of $800. So that's our minimum cost to build this garden. All right. Yeah. Similar to the example from the previous video, here we had two equations relating on two variables of interest. One that we're trying to optimize and one that we had to formulate from the given information. And then we had to use that prior information to rewrite the equation that we're trying to optimize in terms of just one variable to help us solve for our two values here. And then since we also wanted to know that minimum cost, then that's where we solve for our critical values, plug that back into our original cost function to obtain that minimum cost. All right, let's do one more here. Let's do one with some more shapes here. Okay, suppose for this problem, we have an open top box with a square base. And suppose for this open top box, we wanted to have a volume of 4 cubic feet. And just given that information, we want to figure out the dimensions of this box that will utilize the smallest amount of material. Okay, we want to figure out what should be the total amount of material to make this open top box. All right, so how do we figure this out? Should have made this a bit, that's fine. All right, so first things first, it tells us that the bottom base has to be square, meaning that the bottom base, we're going to assume the side of each base, and assume the base here are going to be all of equal length. So let's call that x here. All right, so x, I'll put on the side here. X is going to equal the length of the side, the length of each side of the base. Let's say this will be x, x. Let's see this, as soon as it's connecting over here, xx. Okay. But we also need to know the height of this box. And let's call that height y. So this will be y, y, y. This will be y there as well. Okay, so let me call over here. So y is going to be the height of the box. Okay. So now what? Well, what else does it tell us? It tells us this open top box is to have a volume of 4 cubic feet. How do we define volume again? How do we find the volume of a box? We recall the volume of a box, of a cube, is found by taking the length times the width. Kind of running out of room here. Times the width times the height. I recall from some algebra here. To find the volume of a box of a cube, or not sure if it's a cube, I have to find the volume of a box of a 3D rectangular shape. We need to take the length times the width times the height. So in our case, our volume, well, we're assuming the length and the width, since it has to be a square base, since the bottom has to be a square base, we're assuming the length and the width are going to be the same. So it's going to be x times x times the height, which we're representing, which in this case we're letting y represent, times y. In other words, our volume can be defined as x squared times y. And according to the information that we want, or the information that's required, this volume has to equal 4 cubic feet. In other words, x squared times y has to equal 4 feet cubed. Okay, but what is it we're trying to optimize here? We're trying to optimize the amount of material that is needed to create this box, meaning what is the amount of material that we need to make the left side, the front side, the right side, the back side, but also the bottom side. Okay, and in this case, no top side because we have an open top box. No top will be required. Okay, so what do we call this then? The amount of material that is needed to make the inside of each side. The area. All right, so we want to figure out what the area of the base has to be. And since the base is square shaped, then the base would just be x times x squared. Then I'm going to figure out the area of each side, where each side is being represented by the side along the base, but also the height, right? Each side, the bottom will be x, the height will be y. So the area of each side is going to be x times y. Okay, which means then the total area of the box, the total material that we need then to create the whole box is going to be, well, what? How many sides do we have? Left, right, front, back. 1, 2, 3, 4 sides. So 4 sides here of x and y. But also got to include the base, the square base, which is being represented by x squared. So the total area of the box will be 4xy plus x squared. Okay, let me call that just simply A for total area. The total area of the box can be defined as 4 times xy, our 4 sides, plus the squared base. So now what? Well, if this is the function we're trying to optimize, once again, we have the issue that this function is in terms of 2 variables, x and y. So we need to rewrite this in terms of just 1 variable using some given information in which we know that the volume has to be 4 cubic feet. All right, so let's use this given information to help us substitute into the second equation. Let's solve for, what would be easier? Let's solve for y. All right, so let's solve for y. So let's write this equation. Solve for y to give us y equals, let's select lime green. Y is going to equal 4 over x squared. All right, so now I'm going to use this to substitute into y into this area function. So now we're going to have a equals 4 times x times y, where y is 4 over x squared. So 4 divided by x squared plus x squared. All right, let's multiply these. 4 times 4 gives us 16, x over x squared. We're going to have one factor of x cancel out, leaving us with 16 over x plus x squared. Or we can write this, trying to make sure I have enough room. We can write this as 16 times x to the negative 1 plus x squared. And why did I do that? Why did I bring that x top? Because again, we're trying to optimize this function, which means the next step, after rewriting in terms of just one variable, the next step will be to find the derivative. All right. So let us find the derivative of this function a prime. All right, so using the rules of derivative of 16x to negative 1 will give us negative 16 times x to negative 2 plus 2x. Okay. And then as we find the derivative, set it equal to 0. So 0 equals, and let me bring this x negative 2 back down. So negative 16 over x squared plus 2x. Now what to do here? How are we going to go about solving for our critical value here, solving for x? Let's move this negative term to the other side. So we're going to have positive 16 over x squared equal 2x. And now let's bring this x squared to the top by multiplying both sides by x squared. So x squared multiplying the left side times x squared on the right side. To give us, so these x squares will cancel out, leaving us with 16 equal 2x cubed. And now let's solve for x here. Divide 2 from both sides to give us 8 equals x cubed. Take the cube root of both sides. The cube root of both sides gives us that x has to be 2. So x has to be 2 feet. All right. So the square base has to be 2 foot each side. Okay, but now we need to figure out the height. All right, and how do we figure that out? We'll plug this, so we did the last example, take what we just found and plug it into our given equation, into the given equation that we have to solve for the other unknown variable. So now we're going to take y, I'll use red. So I'm going to say y equals 4 divided by 2 squared, which gives us y equals 1. So y has to be 1 foot. Okay, so y equals 1 foot. So if the square base, if the side of each square base is 2 feet and the height is 1 foot, then that will minimize the amount of material that we need to make this box, which has to have a volume of 4 cubic feet. Okay, so what will be the total area? Well, to find the total area then, take what we found for x and y and plug into the function that we're trying to optimize. So 4 times x, which is 2, times y, which is 1, plus 2 squared, to give us a total area here of 12 feet squared. Right, 8 plus 4 gives us 12 feet squared of material to make this open top box. Okay, and that concludes this section of optimizing problems here.